Good day, I'm Norman Wildberger. In this video we want to start looking at some of the logical challenges that lie ahead of us when we want to set up abstract algebra correctly. Now, abstract algebra these days is not as fraught with difficulties as is modern analysis. Modern analysis has through and through logical difficulties. Abstract algebra, much less so, but still there are some very significant problems. And today we want to start talking about that. Okay, so modern abstract algebra, it's a 20th century development, more or less, and it explores generalizations of rather concrete, explicit arithmetical or algebraic structures. And the logical weaknesses I would like to frame in terms of sort of three different kinds or categories. So the first one that we're going to talk about today is this interaction between definitions and specifications. It's a subtle thing to try to enunciate because we don't have a good language for dealing with these kinds of problems. But I hope to give you lots of examples of the difficulty with, first of all, being precise about definitions and relating that to what do we actually do when we want to specify an object that satisfies a given definition. Then after that, we are going to also talk about the important challenges in going from the finite kind of situation to a so-called infinite situation without waffling. And then another very key problem with modern abstract algebra that runs through quite a lot of it is this over-reliance on the so-called fundamental theorem of algebra. That wouldn't be a problem if the fundamental theorem of algebra was really a theorem, but in fact it's not. It's more of a dream, okay? So we are going to have to face up to the music that the fundamental theorem of algebra has serious problems and how to reframe a lot of the dependence of abstract algebra on the fundamental theorem. Okay, so in today's video though, we're going to stick with this very interesting question of, how do we define abstract algebraic objects and what do we really mean by those definitions with the phrases that we use, with the framework that we have in place. So to frame this first challenge that's really centered on the role of definitions in the subject, maybe it's good to introduce it via this question by trying to identify what's actually the difference between a description, a definition, and a specification. These words are all kind of overlapping and they have some common ground, but what exactly do they mean? And when we define something, are we really defining it or are we rather describing it or specifying it? And to put that question into maybe a more explicit context, we could ask this other kind of question about how do we actually define or specify an algebraic structure for a computer? So suppose we're interested in getting our computer to understand what we mean by, say, a group G. So we have an idea of what a group G is. Suppose that we're actually interested in programming a computer to understand what a group is in the same kind of way as we do. What do we have to do? How do we have to frame the definition? So this is a very good question for a number of reasons. First of all, that the role of computers, of course, is increasing dramatically quickly, and it's going to play more and more of a major role in mathematics. That's something that we're going to have to talk about in the future as well. Another reason is that beginner students who are just coming to the subject, who have not any experience with abstract algebra, seeing these definitions for the first time, in some sense they have similar problems as does a computer. Right? They don't have a prior history of intuitive examples or prior familiarization with things that they can lean on. They really require the definitions to be standalone and self-contained and precise enough for them to be able to distinguish when something is satisfying the definition and when it's not. So there's some kind of parallel between beginner students and computers. They both do not have the kind of intuition that a more experienced mathematician or student might have. So in order to be as specific as possible, let's consider the relatively simple example of a group and how we might define what a group is. Okay, so I'm going to give you a couple of different possible definitions so that we get some kind of idea about the possible scope of possibilities for defining things. Okay, so we want to know what is the definition of a group G. How are we going to introduce that? And our first answer to this, answer number one, is going to be very strongly computer oriented. So this is a definition that we might give if we're aiming to try to get our computer to understand what is a group. Okay, so here's an example, here's a motivating example. Okay, we see a multiplication table, and the objects that are involved are the numbers 1, 2, 3, and 4. And this multiplication table is a way of telling us that 2 times 3 is 1, for example. Okay, so motivated by this, we'll say that, here's our definition, that a K group G, K now is a natural number greater than 1. So K is 1, or K is 2, or K is 3, or K is 39, something like this. So a K group G is a K by K array from K with certain properties. Okay, so before we get to the properties, what are we talking about? We're going back to our earlier discussion about arrays. And I remind you that an array was something like a matrix, but ultimately was different. So an array, which we can think of in this case as being this little 4 by 4 block, this would be the K equals 4 case. So this is a 4 by 4 array, which we can think about as being a list of lists. So that list, followed by that list, followed by that list, followed by that list. Okay, that's what we think of when we think of a 4 by 4 array. Okay, and this array is called a G. And in order for this array to be actually a group, or a K group, we wanted to have certain properties that correspond to the associativity, the existence of an identity, and the existence of inverses. Those are the three main properties that define a group. Okay, so we don't need to pay too much attention here. I just give some kind of official definition. It's actually not so important for us, but let's do it anyway. So the first one, which is a way of expressing associativity, is to say that the group array, G, if we look at the indexes here, G, L sub m, and here N, so there's two indices that give you the positions of the array. For example, this thing here would be the 3, 4 entry. Okay, so the statement is that if you look at the LM entry and then followed by the N entry, so in other words, we're really taking the product of L times M and then multiplying by N, that should be the same as the entry that you see when you look under the L and MN entry. So G sub L comma GMN. And that should be true for all L, M, and N within our range from 1 to K. Alright, so that's some way of expressing associativity in terms of the entries of this array. The existence of the identity is perhaps easier. We'll specify that G sub 1 comma L is equal to L, and also G sub L comma 1 is equal to L for all L between 1 and K. This is telling us that the 1 object, the number 1, is the multiplicative identity in this group. So the numbers are all 1 to K, and 1 is playing the role of the identity. So 1 times 1 is 1, 1 times 2 is 2, and so on. And similarly, 2 times 1 is 2, 3 times 1 is 3, and so on. And this third property is telling us about inverses, that for every index L between 1 and K, GL comma M equals 1, and Gn comma L equals 1 for some M and some N in the range. That's expressing the idea that along every row there's some entry with entry 1, and along every column there's some entry with the entry 1. And that's telling us that every element has a multiplicative inverse, both a left inverse and a right inverse. Okay, so we don't really need to worry too much about the details. These are properties of a particular K by K array. The main point is that, first of all, the array is a very specific array involving just the numbers from 1 to K. And secondly, that in principle, the properties are very cut and dried in that a computer could be programmed relatively easily to check whether a given k by k array from k was actually a group or not. So this is a very computer-friendly kind of definition of what a group is. But it's not the only kind of possible definition that we can think about. Okay, now here's our second definition. It's a little bit more human-friendly and perhaps a little bit less computer-friendly. Let's call it A2. So we're still going to define a K group. K is a natural number bigger than or equal to 1. So a K group G is now a K ordered set, or O set S, together with a K by K array, say capital A, from S, with certain properties. Okay, the properties are going to reflect the usual associativity, identity, and inverse properties that a group needs. But in this setup, the starting point is, first of all, an ordered set. For example, perhaps the set is the numbers 1, 3, 7, 9. Notice that we have commas here, so our convention is that this is representing an ordered set. And we have braces here, that means that no repetitions are allowed. So here's an ordered set which happens to have 4 elements. 1, 3, 7, 9. And together with that set, here is an array that's basically telling us the multiplication table that we want to give this set. So it's an array, in this case a 4 by 4 array, and it's from S, meaning that the entries are all from our set. And okay, so there's a list, and another list, and another list, and another list, and these lists are telling us how we multiply by 1, by 3, by 7, and by 9, following the order of the points or the elements in our ordered set. So we're using the fact that these things are ordered to give a prescribed order in which we're placing the rows or the columns of this array. So in fact, this is the group that we have seen before. This is U10. This is the set of numbers less than 10, which are relatively prime to 10. Things that don't have common factors of 2 and 5. And this is the multiplication table mod 10. Okay. Now, in terms of the properties, well, this array should have certain properties. It should have an associativity property, which is the same kind of thing that I defined previously, and one can define it in terms of this array in sort of a similar kind of way. And we want one of the elements of S to be the identity. This is now a little bit different from previously because we're not necessarily having the numbers here be the numbers 1 through something. In principle, this set S can be rather arbitrary. So we need to specify that one of the elements of S has the identity property. Now in this case it happens to be the number 1, but we don't need to have the number 1 in our set, and we don't need to have it be the first one. Okay, somewhere there's an identity. And each element then has a left or right inverse, and that means that once you have identified the identity, in this case 1, but maybe it's something else, then you see that every row has a number 1 in it, and every column has a number 1 in it. Okay, so this is more flexible because we are not insisting that the actual objects be the numbers from 1 to k. And this is in keeping with the human-centric view on groups, that really, groups come from a wide range of different situations. Sometimes we have groups coming from number theory like this, in which case the numbers naturally are not the numbers 1 to 4, they're the numbers 1, 3, 7, and 9. In other situations, we're considering maybe matrices. The group elements might be matrices. In other situations, the group elements might be permutations. In other situations, the group elements might be transformations, which are actually given geometrically. So this framework is much more flexible in that the actual objects that are, the basis of the algebraic object, the group, are in fact quite arbitrary, at least in principle. However, there's a corresponding challenge with this approach. which is that we have to have a prior theory of O sets. Right? So we're saying a K O set S, but we're not saying that the objects have to come from some specified domain. We're being open-ended about what kinds of elements can be in our set S. And that means that we have a problem in specifying or limiting what kinds of objects are allowed. For example, maybe someone comes along and looks at our definition and says, okay, I've got a new kind of a group. I'm going to let my S be the set of all fish. Set of all fish. That's going to be my set. And the multiplication is going to be, and then I specify some rule, that the product of fish F1 and fish F2 is the fish F3, which is nearest to the midpoint of F1 and F2, or some crazy thing. Okay. So would we allow that kind of situation where the set S is some kind of set which maybe we don't generally consider to be an honest set? In other words, we have to have a prior theory of sets in order to really make this solid. And as we've talked about before, that's in fact quite challenging to first lay out what the boundaries are that separate honest sets from make-believe sets, or almost make-believe sets, or almost honest sets, and so on. So, although this is more human-friendly, a computer would find this much more challenging to deal with because, first of all, of the ambiguity in the nature of the set S, and also because there's less structure with it. We're not guaranteed that the first element is the identity, so we have to search around for an identity. We don't know where it might be. It's a little bit less structured, tougher for a computer to deal with. But it's an alternative. Okay, now here's our third definition, which is even more flexible. So we're kind of zooming out. Even more friendly in some fashion. So we'll call it A3. And the definition is that now a group G is a set S. No longer an ordered set, just a set. Together with a function, say M, from S cross S to S, with certain properties. Okay, S cross S, that means lists of elements of S, two lists. So pairs of elements of S. So for example, here is a set S, 3, 1, 9, 7. This is now a set because it doesn't have commas. It's not ordered. So we can move the elements around and the set hasn't changed. And here is the multiplication. Okay, we don't have an array now. We're thinking more of a function from this set of pairs to S that represents the multiplication. And okay, typically set theorists like to encode functions like this, at least formally, with some kind of framework that's in this direction. So what we could do is we could list all possible pairs of elements here and the corresponding function value of M. So let's say this little entry here is telling us that 3 times 9 equals 7. That's representing one particular element in the array that we wrote down before. So now we've encoded the multiplication not as an array, but as a more in sort of the function point of view, using more or less standard set theory kind of ideas of how to encode a function. Okay, so then of course there's the question about the properties, the three properties, and we would have to then say what the three properties are that this set and multiplication satisfy. Again, we have to build in associativity and the existence of an identity and the existence of inverses. But we could use this language that's even more flexible because now we have just a set and we don't necessarily have an order to the set. And also the multiplication is now a little bit more unstructured, that we just have this function and we haven't necessarily organized the function into an array. We haven't listed things. We've just given all the information sort of all at once in terms of this big set of lists. Okay, so this is just another approach to what a group is, another way of thinking about what the definition of a group is. And now I want to consider a variant of that. So it's going to be a very close variant, so we're going to call it A3 prime instead of A4. And the actual definition is exactly the same as A3. So a group G is a set S together with a function M from S cross S to S with certain properties. But what's different is that we're going to interpret this differently. Or we're going to interpret it in a more broader, looser fashion. So here's an example. Now I'm going to consider the set S, which is rotations of a square. Here's a square. And I'm going to consider the set S of rotations of a square. Now hopefully you know what that means. Hopefully you know that, okay, we're talking about rotations of the square. There's actually 4 rotations of the square. There's the identity rotation, which doesn't do anything. There's a rotation by a quarter turn, by a half turn, by a 3/4 of a turn, or if you like, a quarter turn in the opposite direction. So there are 4 rotations of this square. But notice that we haven't really specified what the rotations are explicitly. We've just said the rotations of a square, and sort of the onus is on you to know what that means. And then what about the multiplication M? Well, here we're saying that the multiplication M is composition. In other words, that the product of S1 and S2, or S1 and S2 are 2 rotations, is the composition of S1 and S2. Okay, so you need to know what the composition is. It means that you do one of them first and then you do the other. Typically here you do S2 first and then you do S1. Now, notice that this is different from the previous example. Here we're not saying precisely what all the rotations exactly are and giving them names. And we're not saying precisely what the product of any specific 2 elements is, as we did in the previous case. Here we're just giving a general rule that allows you to calculate the product of any 2 elements. So in some sense, this interpretation of the definition shifts some of the onus of creating this group on the reader. Okay? You are now invited to write down the elements of this set in some notation that you can introduce, and then you are invited to understand what this composition amounts to in terms of those objects. So you can see that a computer would have more of a difficult time with this, because a computer would have to know how to interpret this, and then a computer probably would want to restate this descriptive kind of definition into something more concrete, either into an array or one of those sort of multiplication sets that we had in the previous example. Of course, there's then also the question of stating the properties, and so we haven't done that. But in addition to saying these things, we would have to specify what the various properties are, the usual associative identity and inverse properties. So it's interesting that this A3 and A3 prime definition, they both actually used exactly the same wording, but there was a difference in interpretation as to what that actually involved. So the question, is there actually an effective or computational difference between these various definitions? Does it really make a difference, or are they all really more or less the same? I want to suggest that there is a difference. There's in fact a very big difference, both theoretical and practical, between defining a group in these various ways. In fact, I want to suggest that group theory is very strongly dependent on which of these definitions you choose. Group theory that starts with A1 is going to be different subject from group theory that starts with A2, which is going to be a different subject that starts with A3 or A3 prime. Currently, I would say that our modern definition of a group, even though people don't spell it out quite as precisely and carefully as we're trying to do here, is more in the direction of this third A3 prime interpretation. We are allowed to specify groups by giving some description of the objects and then some description of the multiplication. We're not really obliged to list all the objects and then to correspondingly list or specify the multiplication in its entirety. So that's the general understanding. Maybe not uniformly, but it's the general understanding in the modern treatment of the subject that more or less this is the right definition or the current definition. But you can see that there's a big difference, or I hope you can see that from a computer's point of view, this is a much more problematic, much more ambiguous. I want to bring the differences between these different points of view into focus for you by looking at a specific example. So let's have a look at U12, which is another group of order 4. So let's start by looking at U12 from the second definition point of view, which is maybe reasonably close to our human perception. So U12, by definition, consists of the numbers less than 12, which are relatively prime to 12. And those numbers are 1, 5, 7, 11. And there's a natural ordering to them because they're increasing, so we may as well list them. So here's an ordered set. 1, 5, 7, 11. And the multiplication is encoded in this array. The array respects the order of the set that we've introduced. And here is the product of these numbers. This is basically multiplication mod 12. But we don't have to say that. All the information is already encoded in this array. And actually the array is just actually this 4x4 block here. These columns and the rows out here that index things is really just for our benefit. But the computer doesn't need it. It just needs that 4x4 array if it knows the order of the objects. So for example, 5 times 5 is usually 25, but mod 12, that's 1. And so we get a 1 there and so on. Okay, so that's a very familiar thinking of U12. That's sort of what we would write down most naturally and simply. But here is a computer version of that, where the computer has come along and said, okay, we're going to encode that not with the numbers 1, 5, 7, 11, but with the numbers 1, 2, 3, 4, because this is a 4 group. It has 4 elements, and so we're automatically just going to use the numbers 1, 2, 3, 4 to represent the objects. And so basically the computer comes along and says, oh, I'm going to call that 1, 2, 3, and 4, and just replaces the 5 with a 2, and the 7 with a 3, and the 11 with a 4. Okay, so there's the same table, but having done that. The advantage now is that the computer can encode the entire group just with this 4x4 array. Okay, you can just send that 4x4 array to another computer somewhere else in the world, and the other computer knows exactly what the group is. Not in terms of its original definition as U12, but in terms of the algebraic structure that encodes the group structure. Okay, in terms of our third definition, the third definition involved a set. So we now lose the ordering. We're not concerned with the ordering. It's just now a set. So I represent that by giving you the same 4 elements, but not necessarily in the usual order. So the objects are 7, 1, 11, and 5. And then we have to record the multiplication in a kind of function point of view. So we have to record that 5 times 5 is 1. So we can do that by somewhere in this list right there, recording the triple 5, 5, 1, and we interpret that to mean that 5 times 5 is 1. So there's now 16 elements in this set of multiplications. This is a way of encoding this array in a kind of a set theoretical point of view. So we have the set and we have the multiplication. And now a quite different variant on that. Now we're going to look at A3 prime, where we describe the set and the multiplication differently. So we say that S is the set of numbers less than 12 relatively prime to 12. That's a description of the set S. It's the same set, but this is a description of it. And the multiplication M, well, that's multiplication mod 12. So you need to know something about relatively prime numbers. You need to know something about how to multiply mod 12 to understand this definition. But if you do, then I guess you could say that this encodes the same kind of information as does this, but perhaps less specifically, less concretely, more abstractly. Clearly this is easier to write down, right? We can write that down very, very easily. And if we replace the number 12 with the number, 12,497, then writing any one of these correspondingly would involve a lot more work. But writing this definition would be essentially almost no more work. We would just replace this 12 with 12,497, whatever we said. So there's some efficiency here, but we have to admit that we're kind of putting some of the specific difficulty in enunciating the algebraic structure under the carpet, or we're imposing the task to the reader instead of doing it ourselves. We're not really giving the group in its entirety, we're giving instructions for the reader to be able to conjure up the group. It's like a recipe for a cake rather than a cake itself. It's your birthday! Congratulations! Here is a recipe for a birthday cake. Okay, thank you. That's sort of what we're doing here. So there's quite a difference between these various things. And you can see that if you wanted to build up group theory as an intellectual discipline, it would matter. It would matter very much which of these definitions, or perhaps some other definition, you adopted. Especially if you were a computer. Okay? If you were a computer, you would have to have a lot of AI underneath your bonnet to be able to make sense of this kind of amorphous, rather wide-ranging definition. While if you were a relatively simple-minded computer, you could deal with this quite efficiently. So we're naturally led to some very reasonable questions as to the meanings of phrases that are very commonly found in modern algebra. In fact, in modern mathematics more generally. For example, the statement, let G be a group. What does that actually mean? Yes, it means that G is satisfying the definition of a group, but which one of our various definitions or interpretations of the definition are we thinking about when we say that phrase? In fact, there may be other definitions that are different from the ones that I've given, or other interpretations. When we say, consider a group G, what do we mean actually? Effectively, concretely, what are we imagining when we say that phrase? When we say, suppose we have a group G. Again, that's a phrase, but what is exactly the meaning of that phrase? And to make that more concrete, we can think about it from a computer's point of view, or a beginning student's point of view. If you're a computer and someone says, consider a group G, okay, well, what does it mean? Hopefully you've been given one of these definitions of a group to begin with, and then you know precisely what it means, especially if that definition was the A1 definition, or possibly the A2 definition along with some additional information. But if it was the A3 definition, you very well may be at C in terms of really understanding what that means. And I think those comments also apply to the beginning student. Even though many beginning students in algebra don't really appreciate that maybe this is part of the difficulties that they find with the subject. So the professor comes in and says, and gives some rather vague or open-ended definition, says, okay, now let's consider a group G. Suppose we have a group G. Let G be group. And the student maybe naturally thinks, well, what does that concretely actually mean? So once a student has spent some years in the academy and is used to using this language repeatedly, they maybe get some kind of intuitive feeling and no longer so strongly require or are confused by it. But I think beginning students find it difficult. What are we actually talking about when we make statements like this? And these statements are very common in mathematics. Okay, so to wrap up, let me give you a more complicated example that really shows how important these distinctions are. That if we stick with small and medium-sized examples, maybe the distinction between these various points of view isn't so big. Maybe we can feel as if we can overcome the hurdles. But if we move towards bigger examples, then the distinctions between these various points of view becomes very clear. We see it in very stark relief. So let's ask the question, what is u of z? Z is our favorite big number, 10 triangle 10 plus 23. And we're after u of z. Okay, so if we take an A1 point of view, the A1 point of view means that we need an array, a k by k array from k, where k is what? Where k is the size of this thing. U of z is going to be the set of numbers less than z, which are relatively prime to z. In order to find the number of elements in that z, these days, you need to understand the prime factorization of z. Without the prime factorization of z, you have no hope of finding the number of numbers less than z, which are relatively prime to z. In other words, the phi of z, the Euler-Tauschig function. Now, we have seen, right, that the prime factorization of z is something that's completely beyond us here in our universe that we're living in. There's no way we're going to be able to write down a prime factorization of z, even though due to the efforts of Joel Sjögren, we understand the first 8 primes. Okay, but the next quadrillion primes we have no idea about yet. Okay, and finding all the prime factors is a completely inaccessible, hopeless problem. Therefore, finding the number of elements in this set is also a completely hopeless thing. And finding actually an explicit array that has all those numbers arranged in a nice way in the multiplication mod z, completely impossible. Like physically, mathematically, theoretically impossible in our universe. So from an A1 point of view, this is a completely undefined object. The computer just stares blankly at you. It says nothing. How about A2? Okay, there we have a little bit more flexibility. We don't actually have to convert everything from whatever we started with to the numbers 1 to k, but we still have to exhibit the objects. We're still not anywhere closer to this thing. We still can't exhibit all the elements in here. There's no way we can exhibit all the elements. First of all, there's far too many. Most of them are numbers that are so big they don't even fit into the universe. Completely and hopelessly impossible. Okay, there's no way that this makes sense. So even a human being that has this orientation just stares at you blindly and says, I'm sorry, but it doesn't make any sense. It's not defined. How about A3? In A3, we were a little bit more loose. We were allowing our set to be actually unordered, not like a real set, and we were still, though, specifying that the multiplication had to be laid out in terms of some kind of function, explicit kind of function in a set theoretical point of view. Again, this is just not accessible to us. But the A3 prime point of view, that's quite different, because there we're allowed to use words and string phrases together. We just say, consider S, the set of n in that, such that n is between 1 and z, and n and z are relatively prime. Voila! There is the set S that the group is supported on. We don't need to concern ourselves with the fact that most of the elements in this set are completely outside our universe. There's no way we can even list them. There's no way we can bring all of these together. There's no way we have any access to this in any reasonable fashion. But nevertheless, we can write down this phrase in a kind of Pollyanna, optimistic fashion. It's like poetry. Look, there it is. There's the set. And what about the multiplication? That's easy. M is just multiplication mod z. You can see the advantages in having a modern point of view on things. If you have a modern point of view as represented by this A3 prime definition, then you have no problem dealing with u of z, because you are allowed to think of u of z in this amorphous, ambiguous, poetical fashion. No problem. As long as no one asks you about any specifics. So as long as you're willing to ride over the actual reality at some suitably lofty level where you actually never get your hands dirty with actually dealing with the objects, just having this abstract point of view, well then you can imagine that you're doing group theory that you're studying U of Z. But your computer has no idea what you're talking about. There's a fork in the road here, isn't there, people? All right? There is this poetical, idealistic, modern 20th century point of view that allows us to just write down stuff like this. And then there's the 21st century computational, explicit, concrete point of view that says, no, that doesn't make sense. I am advocating that we think about things in a more computational, precise, explicit, concrete form, and give up on the 20th century abstraction, ideology, and wishful thinking encoded in this kind of object specification. So the lesson is that definitions and their interpretations do matter. And this is going to be a very important theme for us as we develop abstract algebra. We are going to have to take very special care about the nature of the definitions that we're invoking. And we want to pin them down to computational reality, so that when someone asks for some examples, we can give them real examples and not fake examples like this. This was only our first challenge, okay? So we still have two more challenges to deal with, namely the transition from finite objects to infinite objects, and we'll have to deal with the fundamental dream of algebra. So we'll have a little bit of things to say about those things in our next video. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.